Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. In the last lecture we began looking at the conjugated systems and an approximate method of chemical bonding, a quantum mechanical method that was proposed by Hckel, and we were looking at the linear conjugated systems starting with, of course, ethylene where there is only a single double bond, that is one double bond, and this was extended to the butadiene 1,3-butadiene where there are two double bonds alternate, single bond and a double bond, and a comparison was made on the energies of the butadiene electrons with the hypothetical system of two ethylenes coupled to each other or connected to each other without any delocalization of the electron cloud. And we found out that the delocalization of the electrons in the butadiene results in this additional stability, and it is up to the order of about minus 30 kilojoules per mole or so. The process of calculating these things in order to account for what we measure experimentally is what the approximation method is all about. We shall continue that in today's lecture by extending this to one slightly longer carbon chain, a 6 carbon chain, 1,3,5 hexatriene, and also look at the more important and more often studied Hckel system, namely the cyclic systems of conjugated aromatic hydrocarbons and extension of that to multiple rings, fused rings such as naphthalene, anthracene, etc. I will not do all of that, but I shall introduce the Hckel method for benzene as part of today's lecture, and then probably leave a number of problems for you to attempt along similar lines. So today's lecture we start with we continue with the Hckel molecular orbital theory. And before we proceed with a new system, let us look at 1,3-butadiene a little bit more. Please remember from the last lecture that we wrote down the wave functions for the 1,3-butadiene in this form, namely the 4 p orbitals associated with carbon 1, carbon 2, carbon 3 and carbon 4, the 4 p orbitals and the numerical coefficients in front of them representing in a sense the amplitude of this wave function. The square of this number is the contribution to this molecular orbital from carbon 1 p orbital. 0.6015 square is the contribution to this molecular orbital from the carbon 2 p orbital, and so on. However, there are signs which tell you that the orbital combinations are done with very specific phase relations between them. Sorry. And if you look at the second orbital, the phase relations are peculiar in the sense the third 5p3 and the fourth one 5p4 come with a minus sign, and therefore the molecular orbital is such that the phi p1 phi p2 they are both positive and this is negative, therefore somewhere along that there is a node right in between p2 and p3 there is a node, and psi 3 has the phase convention phase relation as given here, and psi 4 has the phases of second and the fourth p orbital inverted. So let us plot these things to get an idea of what is meant by the nodal plane, and if there is one. So let us see psi 1, it is 0.37, so the phi p1 has a smaller contribution, p2 and p3 have larger contributions, p4 the same as p1. So let us plot that. Okay. Psi 1, I would say p1 with a plus minus a carbon 1 smaller contribution, and p2 is a larger contribution. They have to be symmetric. Let us do that and get rid of this part roughly. It is larger because the numerical coefficient in front of this is bigger. So it is also with the plus sign, and the third carbon has exactly the same numerical coefficient as in the second carbon. So this is also plus minus, and the fourth carbon has the same numerical coefficient as in the first carbon, so it is plus minus. So this wave function, all the p orbitals are in the same phase, and therefore the electron density when you square this coefficient and plot the electron density, it is a sort of an oval shaped. Now psi 2, if you look at the contribution of the individual p orbitals, psi 2 has larger p1 larger p4, but p3 and p4 are negative. So let us keep that in mind. Psi 2 is larger p1 plus minus smaller p2 smaller p3 and larger p4. Well, these are 1 and 4 have the same contribution, 2 and 3 have the same contribution, of course reduced, and let us see the signs again. The signs are plus plus minus minus. So what we need to do, plus plus minus minus, and this of course is plus. Therefore you see that the wave function changes sign from this p2 orbital to this p3 orbital, carbon 3 p orbital, carbon 2 p orbital. Therefore the wave function goes through a node, and the plane that separates carbon 1, carbon 2 from carbon 3 and carbon 4 is called a nodal plane. Okay. What about psi 3? Psi 3 has again 1 and 4 larger, so it is the same picture, but 2 and 3 negative. So all that we need to do for psi 3, 1 and 4 larger, 2 and 3 smaller, but 2 and 3 the way we looked at it, what was the negative sign? The sign was 2 and 3 were negative, minus and minus. So if you are looking at the signs here, so if it is minus, 2 is minus, 3 is minus, first one is plus, first one is plus, fourth one is plus, minus, of course minus, plus, plus. So you see that there are two nodal planes here, because the orbital is negative throughout between 2 and 3, The probabilities are of course the squares of them, so we do not need to worry about the probabilities. Probabilities will never become negative. Okay. So you have two nodal planes. Okay. Psi 3, this is psi 3, psi 4. So it sort of tells you that this is clearly bonding. This is less bonding, there is a nodal plane, but still the carbon densities are such that there is symmetric between I mean there is a symmetry of the electron density right reflected from the middle of the C1, C2, C3, C4 chain. But what about psi 4? If you look at psi 4, that has also two nodal planes. You see it is one smaller, 2 and 3 larger. So first let us capture that picture, 2 and 3 larger, 1 and 4 are smaller. So one, let me just draw that, 2 and 3 are larger, one and 4 are smaller of the same size. And if we look at the signs, 1 4 small, 2 3 large, 2 is negative, 4 is negative. So what we have in this picture is 2 we have to mark negative, 4 we have to mark negative, and 1 and 4 positive, positive, positive. Okay. Let us look at that. You see the difference between 3 and 4. There are still two nodal planes here because the orbital changes sign between carbon 1 and carbon 2. The molecular orbital has the 2p orbitals with different signs, and there is also a change in sign. I guess there is also a change in sign here. Plus minus, plus minus, plus minus, 3 nodal planes. So clearly this is also anti-bonding for this group of 4 electrons, anti-bonding. I mean you have to be careful about these phrases, but the point is that the electrons, the 4 electrons are likely to be in orbital psi 1 and psi 2 for the other reason that psi 1 and psi 2 have the lowest energies. Please remember alpha and beta are negative. If alpha and beta are negative, obviously the sum of alpha plus 1.618 beta is negative, and the second orbital is also negative. Therefore the 2 electrons in orbitals with the wave function psi 1 and 2 electrons with the wave function psi 2. So you have all the 4 electrons in that orbital. So it is clear that the 4 electrons are placed accordingly, and we also looked at this by way of looking at the HOMO-LUMO gap and so on. Okay. So you can see that the 4 psi 1, psi 2, psi 3 are I think I have already done that before, so let me not repeat that here. Okay. Now there is one other thing before we move on to the cyclic system, namely what is the charge density on each of the carbon. I mean we should have some reason to believe that the electron density on each of the carbon should be the same, otherwise there is going to be differences between the bonding capabilities and the bond lengths perhaps, and in 1,3-butadiene we have only one carbon bond. So the charge density, the way we calculate the charge density is you look at the wave functions here, these 4 wave functions. Since the electrons are there in the first orbital psi 1 and psi 2, but not in the orbital psi 3 and psi 4, the orbital psi 3 and psi 4 would not contribute to the electron density, they are empty orbitals. The orbitals 1 and 2, molecular orbitals psi 1 and psi 2 would contribute to the total electron density calculation. By how much? If you look at carbon 1 in psi 1, It is 0.3717. So therefore the square of this represents the probability that the electron is in phi p1. The 0.6015, the square of that represents the probability that the electron inside 2 molecular orbital is found in phi p1. Therefore if you think about carbon 1, the total electron density is the sum of these squares, because these two represent the probabilities of finding the electrons in orbital p1 corresponding to carbon 1, due to the fact that the electrons are either in psi 1 or in psi 2, in this case both in psi 1 and both in psi 2. How many electrons? There are 2 electrons in psi 1, there are 2 electrons in psi 2, therefore the total charge density that you have to calculate would turn out to be, for carbon 1, the contribution to phi p1 in psi 1 plus the contribution to phi p1 in psi 2. Okay. There are 2 electrons here, there are 2 electrons here. The contribution to phi p1 is the probability square, which is what was that? Psi 1 was 0.3717 square. So 0.3717 square, and since it is to be multiplied by the total number of electrons, which is 2 in this case, and the other for phi psi 2, if you look at it, psi 2 it is 0.6015 square, and again 2 electrons in psi p2, so it is 2 times 0.6015 square. So this is the total charge density on each of the carbon, in this case carbon 1 is the sum of this, and this is of course equal to 1. Please remember, this is how we got the normalization constant. Any one of these, square, 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 add them all up, it is 1, and that is what you have. Likewise, if you calculate the charge density on C2, it is a contribution to phi p2 contribution of phi p2 to psi 1 plus contribution of phi p2 to psi 2, and each of this contribution is multiplied by the total number of electrons in each of these molecular orbital, which is 2, and you will find that to be exactly 1. And likewise for C3 you will get the total charge density to be 1. And for C4 also the total charge density to be 1, which means that on each of the carbon the total charge density of the electron density, if you look at it, on each of the carbon is 1 for both these molecular orbitals, which means that there is homogenization. Okay. So this is another way of understanding what is called the delocalization in terms of the electron charge densities. In terms of placing the orbitals of course come with the plus minus signs to tell you that these orbitals are orthogonal to each other, and they represent the node or anti-node character or bonding and anti-bonding character, similar to what we did in the case of the hydrogen molecule ion and hydrogen molecule. So these pictures are very useful, but to a limited extent, and HÜckel molecular orbital theory gives you this very nice way of pictorially representing the molecular orbital and the electron charge densities, and at a time when of course computers were not available, at a time when computational power was non-existent and so on. Today we like to teach HÜckel molecular orbital theory for some of the concepts that are introduced in the process. It is not probably as useful as doing a brute force many CPU calculations. It does not matter, it is important to understand the basic principles of computational chemistry, and HÜckel molecular orbital theory is a cornerstone in that sense. Okay. Now since we are running out of time, I am going to write the linear chain 1, 3, 5, what is this, 1, 3, 5 hexatriene very quickly and leave you with the electron density sort of homogenized. Okay. There is nothing called a plus or minus for the electron density, both up and down are the same. So if you do that, the Hckel matrix as an exercise, I would want you to derive that, and let me write the Hckel matrix very quickly. It is x1, sorry, let us go back, it is x1 0 0 0 0, it is 1x 1 0 0 0 0 1 x 1 0 0 0 0 1 x 1 0 0 0 0 1 x 1 0 0 0 0 1 x. Okay. All these matrices are tridiagonal. Let me just get rid of that. All these matrices are tridiagonal. Let me see if I can draw that line. You can see that one off diagonal here and one off diagonal here. Okay. Tridiagonal matrices. Eigenvalues can be easily obtained. There is a general expression for this in textbooks, maybe in the assignment I will give you that expression for you to calculate, but the energies are known, the eigenvalues are known, and you can calculate the charge densities the same way that we did a few minutes ago. You can also write the wave functions that appear with a plus minus sign depending on how you solve the eigenvectors and so on. Therefore, I leave this problem to you to study the all these aspects as an assignment. Now let us get to the other important aspect, namely the cyclic systems, and we will start with the aromatic we will start with the first system, namely cyclobutadiene. Okay, cyclic systems, cyclobutadiene. Okay. Picture 4 carbons, and now you can't tell which is 1, which is 2, which is 3, which is 4. In a linear chain you had terminal carbons and you had carbons in the middle, so your numbering made sense. Here my 1 2 3 can be your 2 3 4 1 and so on. The point is that with one label we will see that the Hamiltonian matrix, the Hckel matrix, has just a small variation from the butadiene matrix. The butadiene matrix, if you remember, is x1 0 0 1 x1 0 0 1 x1 0 0 1 x. This is for butadiene. Now cyclic butadiene, you see that the atom 1, carbon 1 p orbital and carbon 4 p orbitals are adjacent, and therefore the 1 4 which was not there in the linear chain because they were far away, this is 1 2 3 4, the 1 4 linear chain, now since it is a cyclic chain you have 1 4 which also contributes a beta term, and therefore this is 1 for cyclic butadiene, and likewise for 4, atom 4, it is 1. That is all there is a difference, the Hckel matrix. So from any linear chain to a cyclic chain, cyclic system, when you go in, the end to end bonding will ensure that the terminal carbons, what you called as the terminal carbons in a linear chain, now will have a Hij matrix element, H1n, Hn1 matrix element. Inside nothing else changes, all the other things are exactly what you had in the linear chain. Therefore this is the only difference between the butadiene and cyclic butadiene and cyclobutadiene, Is that what I said here? Yeah, I have said that, yes. So in the cyclic system you have that, and its eigenvalues can be written down. So the eigenvalues for cyclobutadiene, when you solve this, basically you are going to expand to this determinant and get the values. The eigenvalues will turn out to be E1 is alpha plus 2 beta, E2 and E3 will be alpha, it is a degenerate system, and E4 will be alpha minus 2 beta. Okay. So if you draw the molecular orbitals for the energies E1, this is alpha plus 2 beta, and then you have alpha which is doubly degenerate. So it is E2, E3, this is alpha, and the number of electrons that we can assign is for the ground state alpha plus 2 beta 2 electrons, and because it is degenerate the spin is supposed to be such that they are unpaired, and then we have E4 which is given by alpha minus 2 beta. And therefore you see that the HOMO-LUMO gap, this is the highest occupied molecular orbital and this is the lowest unoccupied molecular orbital. The HOMO-LUMO gap is obviously 2 beta. Okay. What are the wave functions? The eigenfunctions for this system? Psi 1 is 1 by 2 phi p1 plus phi p2 plus phi p3 plus phi p4. Okay. Then psi 2, there are two ways of doing it, psi 2 and psi 3. In principle, if we do a symmetry group analysis, we will end up getting the 1 by 2 with 2 positive signs and 2 negative signs, and there are 4 such combinations. That is one way, but let me do the other way around, which is write the psi 2 as 1 by root 2 phi p1 minus phi p3, and psi 3 which is degenerate to psi 2 will have the other 1 by root 2 phi p2 minus phi p4. I will tell you in a minute what this leads to, and psi 4 is of course you have 1 by 2 times phi p1 minus phi p2 minus phi p3 and plus phi p4, I think, sorry, minus plus minus, sorry, it is minus phi p4. Okay. Well, the reason why we choose this instead of taking the 4 linear combinations, all the 4 orbitals, is pedantic in this case, of course, because you see that psi 2 and psi 3 correspond to degenerate orbitals, and if you are talking about degenerate systems, the 2 wave functions corresponding to degenerate systems, any linear combination of those 2 wave functions is also an eigenfunction of the same Hamiltonian. Therefore, in principle you can have all the 4 orbitals with the plus minus signs done in such a way that if I write a coefficient of 1 by 2 outside with 1 1 1 1, and these are the weights given to the orbitals phi p3 phi p4, then in principle I can have 1 1 minus 1 minus 1 1 minus 1 minus 1 1 1 minus 1 1 minus 1. Now you saw that it is all 1 by 2 multiplied, so this is also a possible way of writing the cyclobutadiene, the atomic, the molecular orbitals with the contributions of phi p1, phi p2, etc. The eigenfunctions in this case, because of the degeneracy, can be represented in multiple ways. Okay. And one way is that contribution phi p1 minus phi p3 and the contribution phi p2 minus phi p4 corresponding to E2, and the other way is that the contribution like this, phi p1 plus phi p2 minus phi p3 minus phi p4 multiplied by 1 by 2, and likewise phi p1 minus phi p2 minus phi p3 plus phi p4 all multiplied by 1 by 2. So it does not matter. What is important is that the eigenfunctions are such that the electron densities when you calculate on each of the carbon, they will all turn out to be the same. Okay. Now the only difference that you have to keep in mind is that the electrons are now contributed, the electrons contribute differently. For example, the wave function psi1 has 2 electrons associated with that, and the wave function psi2 and psi3 have 1 electron each associated with that, and therefore if you are looking at the carbon 1 electron density, you have to multiply the coefficient of Ip1 on psi1 squared, coefficient squared, by 2 because there are 2 electrons in psi1, and the psi2 and psi3 contributing 1 electron, you have to multiply the corresponding coefficient squared by just 1. So here for example if you do that, it is 1 by 4 multiplied by 2 and 1 by root 2 squared multiplied by 1. The psi3 does not have any phi p1, therefore you will have 1 by 2 plus 1 by 2 which is 1. So the electron density still turns out to be the 1. Ultimately it is the electron density and its properties which are important. The wave functions are such that the square of the wave functions have the meanings of probability interpretations. The signs of the wave functions are important in determining bonding, anti-bonding kind of a concept, but the coefficients themselves do not have any other interpretation. It is their squares, and therefore the signs and linear combinations can be chosen conveniently. Okay. So this is for cyclobutadiene. Let us go quickly to benzene and finish this part of the lecture and leave you to study Hückel molecular orbital theory in more detail on your own. Okay. Let us do benzene. 6 carbons, or your original Hckel structures, whichever it is. We know in molecular orbital picture or in the quantum mechanics that we can't distinguish between these carbons. The Hückel matrix now is the same starting matrix like what we had earlier for the tridiagonal matrix for the 135 135 hexatriene, except that we are going to add the 2 terminal portions 1,6 and 6,1 to 1. Okay. So what is the Hückel matrix therefore? For benzene it is X1,0,0,0,1 because the 6th carbon is bonded to carbon 1. Then you have 1 X1,0,0,0, 1 X1, these things do not change, the near neighbors are only the 2 neighbors on either side, 0 1 X1 0, 0 0 0 1 X1, and now on the 6th row you have 1 here 0 0 0 1 X. Okay. Okay. This is the determinant that you want to set, and remember X is equal to alpha minus E by beta. Okay. So the energy E is there. What are the solutions? Okay, expanding this determinant is your pastime, and obtaining the secular equation, it is an assignment, please do it, and the answer that we get for benzene, let me write down the answers. We get again 2 degenerate states. In fact, that is a general theorem that when the molecule has a symmetry of more than a certain type on rotational axis, it will have degenerate states, but those are all things we will do when we go to group theory. Right now these 4 energy levels that we find with the degeneracies are E1 is alpha plus 2 beta, the lowest energy, E2 and E3 is alpha plus beta, E4 E5 is alpha minus beta, and E6 is alpha minus 2 beta, and there are 6 pi electrons. So, assigning them carefully will give rise to this picture that we have 6 electrons in the first 3 orbitals, and this is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital, and therefore, you see that the delta E, the HOMO-LUMO gap, is 2 beta again. Okay. What is the resonance energy or delocalization energy? The difference between the energies of the 6 electrons minus the energies of the 6 electrons, assuming that bonds are, the double bonds are localized. So, if you calculate that, in the case of ethylene, if you remember, the resonance energy, 3 localized ethylene bonds is going to give you 6 into alpha plus beta, and benzene, you have 2 electrons in alpha plus 2 beta, 2 electrons in alpha minus plus beta, and 2 electrons in alpha plus beta. Yeah, so alpha plus 2 beta. So, if you look at it, the difference between these two is again 4 plus 2 plus 8 beta, this is 6 beta, the alphas cancel out, resonance energy is 2 beta. Okay. So, what about the molecular orbitals for benzene? The expressions are long, but let me write them down. Psi 1, which has the energy alpha plus 2 beta, is 1 by root 6, very symmetric, phi p1 plus phi p2 plus phi p3 plus phi p4 plus phi p5 plus phi p6. It is normalized. You can see that the contributions of the individual orbitals, phi p1 square, phi p2 square, each one is normalized, and therefore psi 1 star, psi 1 deta. If you do that and neglect the overlap which we did in the Hckel molecular orbital theory, it is 1 by 6 multiplied by 6, and therefore the wave function is normalized to 1. What are the other 5 orbitals? Let me quickly write them down and also write the pictures of some of them to give you an idea of what are the nodal planes and so on. So, let us look at psi 2. It is 1 by 2 phi p2 plus phi p3 minus phi p4 phi p5 minus phi p6. Okay. Psi 3 is 1 by root 3 times phi p1 plus 1 by 2 phi p2 minus 1 by 2 phi p3 minus phi p4 minus 1 by 2 phi p5 plus 1 by 2 phi p6. Okay. These are both are degenerate orbitals, and therefore, in principle 2 orthogonal linear combinations of these two will also form the corresponding molecular orbital. Psi 4 is, you can write from psi 2, it is 1 by 2 times phi p 2 minus phi p 3 plus phi p 5 minus phi p 6. Okay. Psi 5 is also written from the orbital psi 3, 1 by root 5 phi p 1 minus 1 by 2 phi p 2 minus 1 by 2 phi p 3 plus 1 by 4 1 by 2 sorry plus phi p 4 minus 1 by 2 phi p 5 minus 1 by 2 phi p 6. And these two are the degenerate orbitals with the energy alpha minus beta. These are with the orbital energies alpha plus beta, and the last one psi 6 is obtained from psi 1 with alternate minus signs, namely phi p 1 minus phi p 2 plus phi p 3 minus phi p 4 plus phi p 5 minus phi p 6. Okay. So, now if we look at the orbitals on the ring, psi 1 essentially means all the orbitals are plus minus, all of them are in the same phase, plus minus, plus minus. No nodal plane, the electron density is such that it does not go through any the electron wave function is such that it does not go through any zeros, okay, between the p orbitals. What about psi 6, which is also easy to draw, because the carbon p orbitals, every alternate p orbital is of the same sign. So, you have plus minus and plus minus, and the other three are negative combinations, minus plus, minus plus, minus plus. Okay. Now, you can see that there is a nodal plane here, the orbital sort of goes through, and it goes through a nodal plane here, and again it goes through a nodal plane. You can see that plus minus, plus plus, and goes through that. You can see that it sort of goes down here. So, you see that there are plus minus, there is a nodal plane, that is a nodal plane. There are only 3 planes, because you can see that this nodal plane is exactly the in a symmetric system, these two is one nodal plane, these two is another nodal plane, and these two is another nodal plane. So, you have a way of looking at pictorially the 6 molecular orbitals of the benzene, and also look at the charge densities on all the 6 carbons. If you calculate it by the way I did, namely take each molecular orbital, determine the square of the coefficient corresponding to the carbon p orbital, multiply by the number of electrons that orbital has, and add them all up for all the molecular orbitals for that single carbon atom. If you add them all up, you get answer 1. We have done that earlier, and you repeat this exercise to verify for yourself that the theory gives you uniform electron density on all the 6 carbons. Okay. So, Hckel molecular orbital theory is a very beautiful approximate theory. Please remember that these things were discussed, developed long before the computers were discovered, and computers were invented, and computational calculations were done. The linear combination of this kind of atomic orbitals to form the molecular orbital, there is an entirely different approach based on the point group symmetry of these molecules, where due to the irreducible representations of the point groups or based on them we can in fact construct some of these linear combinations. You will see that the results are exactly the same. That is a different way of doing it. Often people think that that is a more elegant way of doing it, but elegance is not a question, I mean it is a question of one's own viewpoint. Ultimately we should be able to compute the molecular orbital, we should be able to calculate the energies and compare them with the experiments in order to do this in a meaningful way that theory and experiments corroborate each other. Therefore in that sense I would say the Hckel molecular orbital theory is a very good starting point for a large number of systems to be studied in organic chemistry, and I will not deal with this any further. An extended molecular orbital approach may be given later in an advanced series of lectures. Until then, thank you very much.